Hello, so today we will be going over the Navier-Stokes energy equation. So the energy equation states that the energy inside of the control volume must equal the internal energy plus the kinetic energy. And to note that ECV is energy in control volume. Internal is internal energy and E kinetic is the kinetic energy. So the internal energy is the following. E internal equals out to be density rho times little e dV, where little e is the internal energy per unit mass. For the kinetic energy, we have rho times the magnitude of the velocity vector squared over 2 times dv. And this will equal out to be 1/2 rho times u squared plus v squared plus w squared dv. So our E internal plus E kinetic will equal out to be rho times E plus V squared over 2 dV. And taking the time derivative of this equation here, we get the following. Partial E CV with respect to time equals out to be partial t of E internal plus E kinetic. That will give us partial E CV partial T equals out to be partial t rho e plus velocity magnitude squared over 2 dV. We'll call this equation 1.1. I'll actually put that in a different color. So, focusing on the energy inside of the control volume, we have, call this 1.2, have dE dot, which is the transported internal and kinetic energy. Say that 1.3 is dQ. The heat transfer say that 1.4 is the energy in the compressive, normal, and shear stresses. And then 1.5, we will call this the external energy. And examples of external energy could be radiation, combustion, or other terms. Equation 1.6 are then body forces. K dotted with V. K vector dotted with V vector. dV. And these are the body forces. So like gravitational, gravity, magnetic, etc. I would like to note that the external energy Q dot S is on a per unit mass basis. So I would like to say that for 1.5 here, I'll write it up here. Q dot S equals out to be capital Q dot S per unit mass. So we'll say that here Q dot S equals rho, big Q dot S equals rho little q dot S dV. So our entire equation will be the following. Partial t times rho E plus the velocity magnitude squared over 2 dV equals out to be d E dot plus dQ dot plus dA dot plus rho little q S dot dV plus the body forces K dot V dot or V hat K hat dot V V vector K vector dotted with V vector. Excuse me. So let's take a look at section 1.2, equation 1.2. Which is the energy. So let's start off by drawing out our control volume. And we'll make this blue. So our energy going in and out of the control volume is illustrated by the following. This is the energy in the x direction. This is energy in the x direction at x. This is the energy in the x direction at x plus dx. And let me create our coordinate system. This is x, y, and z. This is the energy in the z direction at z. This is the energy in the z direction at z plus dz, and then same goes for the y direction. So, excuse me, with our control volume here, we can say, looking at the control volume, we can say that the inlet energy is the following. Rho E plus the magnitude velocity squared over 2 times U, because that's this is the energy multiplied by velocity in the x direction times the area that it that the energy is traveling through, and the area would be dy dz. The outlet energy would be the following. Rho times E plus V squared over 2 U plus partial x. This is the energy going, the energy at x plus the energy at dx. E plus velocity magnitude squared over 2 times U dx dy dz, because they're both going through the x plane. Similarly, for the y direction, have rho E plus V squared over 2. We have V dx dz E dotted with y plus dy equals out to be rho E plus velocity magnitude squared over 2 times V plus partial y rho E plus V velocity magnitude squared over 2 V dy dx dz. Lastly, for the z direction, z is rho E plus velocity magnitude squared over 2 W dx dy. For the outlet, E dot z at z plus dz equals out to be rho these are partials. dx dy. All right. So dE equals out to be the energy, the inlet minus the energy out at the outlet for all three directions. U dot x at x minus E dot x plus dx y dot y at y plus dy plus the last one for z plus dz. So dE dot equals out to be negative partial x rho times E plus velocity squared over 2 times U plus partial y rho times E plus V squared over 2 V plus partial Z rho E plus V squared over 2 W dV. Now we can move on to 1.3 with the heat transfer. So again, we'll draw out another free body diagram, and let's actually take this free body diagram. I think we can copy and paste it, save some time. Perfect. Save some time, put this here, then we can get rid of the E terms. And essentially we are finding the heat transfer going in and out of our control volume. Q dot, Q dot. And I just noticed that there's not a dot above the E here. Good to catch that. X. Perfect. So we have our heat transfer through the control volume, and we can repeat the same process. I would like to note first that I'm going to make it a little bit easier. Can move this whole thing off to the side over here. And that the heat transfer follows Fourier's law. which states that Q dot equals negative lambda A gradient T, where Q dot is the heat flux, lambda is the thermal conductivity. You might also recognize the thermal conductivity being K. However, we already denoted K to be the body forces, so that's why we're using lambda as the variable for thermal conductivity. And I should say that heat flux has a unit of watts. Thermal conductivity has a units of watts per meter Kelvin. A is the cross-sectional area, which obviously has units of meter squared or length squared. And then gradient T has is the temperature gradient. Which has units of Kelvin over meters. And one little quick note I would like to highlight is that this negative sign in Fourier's law indicates that this equation is following the second law of thermodynamics. Second law of thermodynamics, that energy at a higher temperature transfers down to an energy at a lower temperature. So moving on, say that the heat inlet using Fourier's law in the x direction equals out to be negative, not K. Negative lambda partial T partial X dy dz, and the heat outlet, excuse me, the heat outlet Qx at x, this is Q dot x at x plus dx, equals out to be negative lambda partial T partial X plus partial X negative lambda partial T partial X dx multiplied by dy dz. And the same thing in the y and z direction. And lastly, in the z direction, this will be dx dy. Plus dz dz dx dy. Then q dot dq dot equals out to be the heat going in minus the heat going out. X at x is at x plus dx plus q y minus q in the y direction going at y plus dy equals, sorry, not equals, plus q dot z at z minus q dot z plus dz. Therefore, dq equals out to be partial x lambda partial t partial x plus partial y lambda partial t partial y plus partial z lambda partial t partial z multiplied by the control volume. Do that for the last one. Yes. Perfect. So that ends 1.3. So now we can look into section 1.4, looking at the compressive, normal, and shear stresses, the energy from those stresses. And since this is a little bit lengthy, we will only look at the x direction and apply the same approaches to the y and z directions. So I'll just give you an idea of what the approach will look like for the x direction first. So let's create our control volume. And I'll make it a little bit bigger this time. Make this a little bit more straight. Say that this is the x, y, and z direction. And we'll take a look at the x direction first. So say that analyzing x direction for example. So here, we'll start off with our pressure P evaluated at x. We have the shear stress on the x plane, but going in the z direction. So this will be called tau xz, and we'll evaluate this at x. This is sigma xx, the normal stress, on the x plane going in the x direction, and this will be evaluated at x. And then lastly, we have tau x y, so on the x plane, but evaluated, not evaluated, the shear stress is going in the y direction. We are evaluating this at x. Alternatively, for the point at x plus dx, say that this is P, the pressure at x plus dx. This is tau xy at x plus dx. This is sigma xx at x plus dx. And then this is tau xz at x plus dx. So you can see why now that I'm only focusing on one direction, because it can get really hectic if we were to analyze in all three directions. So for the x direction, we'll have at x, we have P of x equals the pressure times dy dz. Actually, let's do this. Pressure times the velocity in the x direction times dy dz, because the pressure has units. This will give us an energy rate of energy with respect to time, because pressure has units of newtons per meter squared. velocity in the u direction has units of meters per second, and area has units of meters squared. So if we were to cancel all the if we were to multiply all the units together, we would get something like Newton meters per second, which goes to joules per second, which is the units for power. So I'll erase that for now. Just a little side note as to why we're multiplying pressure and U together. That's where the U comes from. For sigma xx evaluated at x, we have sigma xx d. We'll also say that this is U. U dy dz. And the shear stresses x, y, evaluated at x would just be tau xy times v, because the force is going, the stress is going in the y direction, times dy dz. Then we have tau xz at x, which equals out to be tau xz times w dy dz. So that is at x. So now we want to take a look at x plus dx. We have p x plus dx, which equals out to be p u dy dz plus partial x p dy dz times u dx. Actually, to make it a little bit more clean, let's say p times u dy dz dx. P, this is sigma xx at x plus dx equals sigma xx times u dy dz plus partial x sigma xx dy dz sigma xx u dy dz times x. Next we have tau xy evaluated at x plus dx equals out to be tau xy v dy dz plus partial x tau x y v dy dz times dx. Then lastly, we have tau x z x plus dx equals out to be tau x z w dy dz plus partial partial x, tau x z, w dy dz times dx. So then could say that dAx dot equals out to be px minus px plus dx minus sigma xx at x plus sigma xx at x plus dx minus tau x y at x plus tau x y at x plus dx minus tau x z at x plus tau x z at x plus dx. And the reason why we have p of x minus px plus dx, the pressure at the inlet minus the pressure at the outlet, is because pressure decreases in the direction of the flow. Pressure decreases in direction of flow. In other words, flow travels from high pressure to low pressure. So that is why we have our equation set up like this. So I'm going to separate 1.4 into 3 sections. So we'll have first 1.4.1. This will be dA dot x equals out to be negative partial pu partial x plus partial sigma xx u partial x plus partial tau x y times v partial x plus partial tau x z w partial x dv. 1.4.2 we'll have dA dot y, and if we apply the same approach as we did for the x direction, we will achieve we'll get to the following. We have partial PV partial y plus partial tau yx u partial y plus partial sigma y v partial y plus partial tau y z w partial y dv. And lastly, we have equation 1.4.3, which is the z direction. And again, we can apply the same approach as we did for x into the z direction, and we'd get the following. Partial p w partial z plus partial tau zx u partial z plus partial tau zy v partial z plus partial sigma z w partial z times dv. So now we can assemble sections that we have just worked with. So we have 1.1 equals 1.2 plus 1.3 plus 1.4.1 plus 1.4.2 plus 1.4.3 plus 1.5 plus 1.6. And doing this, we would get the following equation. Partial t rho e plus squared over 2 dv equals out to be negative partial x rho e plus v squared over 2 squared times u plus partial y rho e plus v squared over 2 v plus partial z rho e plus v squared over 2 times W plus this will be partial X. This is the heat contribution, not K, this is lambda. Partial T, partial X, plus partial Y, lambda, partial T, partial Y, plus partial Z, lambda, partial T, partial Z. Plus our terms here. Well, that didn't go well. Here we go. So copy and paste. These terms plus rho QS dot plus K vector dotted with V vector times all multiplied by dV. And notice that dV appears on the left-hand side and the right-hand side of the equation. Therefore, we can cancel these terms out. And we have our preliminary equation. There's still a lot of work that needs to be done. However, I will be stopping the video here just due to time and computer storage on my laptop. So I will be having a part 2 to the energy equation, deriving the energy equation. So I will have these notes uploaded and there will be a link down in the description below for free. And if you have any questions or comments about the derivation process so far, please shoot them down below. And I'll have the second part of the energy Navier-Stokes equation up as soon as possible. And I would like to thank you so much for your attention, and please have a great rest of your day.